Now, the complications of this are really not complications, because I've got a method of teaching it to you that really kind of leaps out of the page for the nature of what we call Chatelier's principle. It deals with the shifting of chemical reactions. Given a certain concentration reactants products, and then you apply what we call a stress to that reaction, then what happens to the reaction? It shifts left or right depending on what you do to the reaction. So that's the theme of what I'm about to give you. So the Chatelier's principle deals with the shifting of reactions when a stress is applied. In a formal statement, and this is paraphrased in most textbooks, Chatelier's principle will state something of the nature like this: if a stress is applied to a chemical reaction in equilibrium condition, the reaction equilibrium will become unstable and shift away from the applied stress. So the question is, what are the stress factors that we are going to apply to various chemical reactions and observe their process of shifting left or right or whatever? These include concentration effects, temperature effects, and pressure volume effects. Now, each of these applied stresses have certain rules with them that are best illustrated in what I call the seesaw method, defining how the reaction is disturbed and then shifts back into a new equilibrium. So in the application of to problems or stress factors, what we'll start with is an original equilibrium plus then apply a stress factor, and this will ultimately lead to a new equilibrium conditions. So in the mental process of working problems and dealing with things of this nature, you have to think, well, where am I and what's happening and where is it going in the context. And you can use the ice table. I'll show you how as you move things around in the process. Okay, when we talk about concentration effects, let's consider a hypothetical reaction. A plus B goes to C plus D, and now that reaction is the original equilibrium. Now, to determine the concentration effects, what you need to do, and there are other ways to do this, but I'm just giving you an approach that has worked well for students over the millennium of my teaching experience. What you need to do is put the reaction on a seesaw, a hypothetical seesaw. So we use a seesaw effect like this. Now, when the stress is applied, it's a concentration effect. And so you're either adding more A or more B or both, or you're introducing more C or introducing more D or both. So from a logical standpoint, what would happen that your experience tells you would happen to a seesaw if you have, say, these are all children on the seesaw, and all of a sudden one got off. Okay? The seesaw would be unstable and tilt left or tilt right, depending on who got off of the seesaw. Or if one got on, or you added an extra A got bigger all of a sudden, instantly, what would happen? You would, of course, tilt to the A side, or if D got larger, you would tilt to the right side. Well, those are unstable conditions. So adding A or B or in the other case, in the other side of the coin is adding C or D, you would result in a tilt left on the AB addition. Okay. Like this, and your tilt right over here. And your condition. So we put our fulcrum in to show and illustrate. Now, one thing to note here, once the stress is added, you are no longer at, or the reaction is no longer at equilibrium. So when you write this, A plus B, C plus D, A plus B, C plus D, you need to ask yourself, what must happen to bring this equilibrium back to a level condition? And so on both of these, we kind of redraw our seesaws showing a level condition like this. And this would be the new equilibriums. Depending on what what happened in the shifting of the reactions. So when you look at these, what must happen? Well, we have to add more weight over here to the right side. So in order to bring this back down to re-achieve this, it tilted left when the weight was added, but it must tilt right to reestablish. That means the reactants must react to make more C and D to make this come down. In that case, and that will occur naturally and that's the natural chemistry of the reaction. It will shift away from the applied stress. See, if you applied extra A, then you notice the arrow pointing to the right will shift away from that additional. It has to reduce that stress and create more C and D by reacting over here and making more CD and making that new equilibrium exist. Now, one thing that in some cases, now temperature will change the equilibrium constant, but changing concentrations in the reaction will not change the equilibrium constant. I'll say that again. Changing concentration effects and pressure volume effects will not change the equilibrium constant. So the equilibrium constant, Kc, in the new will be the same as the Kc old. But temperature effects will, as a matter of fact, change those. We'll talk about that when we get there. But pressure, volume, stresses, and concentration effects do not change the K value. So if you have the new equilibrium, and if you have Kc, you can determine what concentrations would be down here in the new equilibrium, given, say, a couple of concentrations of reactants has gone to such and such. Well, whatever the reactants lose is added to the products. And so you can calculate the concentration of reactants and products at the new equilibrium condition. Right? We'll get problems on that. Well, in this case, we see the seesaw has tilted to the right, but must shift left to add more A, B weight. If we added C or D, say we added D, then C and D must combine to form AB, like that. Now, this is adding. In the concentration issue, you can also evaluate the reaction process or affect the reaction process by removing stuff. If I removed A and B, what would happen? If I removed C and D, what would happen? Okay? If we remove chemicals from a reaction process, then that would be a concentration effect, and the effects would be to lighten that side that the chemical is removed from. For example, if we remove A or B from this reaction, of course the left side would be lighter, and the CD would cause a tilt to the right. And if you remove C or D, of course you would have a left tilt. Now, when you look at the tilt, you decide on which way will it shift. The shift is going to be, in the first case, to the left, or in the second case, to the right. Now, that's kind of an obvious conclusion, I would assume. But what you also should think about in this is what's happening to concentrations in that process of shift. So if this one is shifting right to left, what are the concentrations of C and D doing? They are decreasing. They would have to decrease. Well, A and B are produced from C and D, so those would have to increase. So in the process of going from the applied stress to the new equilibrium, C and D concentrations decrease, and A and B concentrations increase. And this will show up in what we call the change row in the ICE table. How do they change going from one to the new equilibriums? And we'll get to that in due time. And the opposite is true over here. That doesn't look like a good C. If we are removing C and D, okay, then their concentrations decrease, and if we remove C and D, this would be your tilt right here. So we have to replace C and D. Okay, so those would be lower concentrations. So we have to increase those. Excuse me, I'm getting ahead of myself here. A and B increase concentration to increase concentration of C and D to make the new equilibrium. And they will have new concentration terms in those. Get this handout and go to 1461. Now, in this problem, you are to determine which way the reaction will shift based on the concentrations that are given in this problem. Now, to do that, there's a little set of rules that is very simple, a little diagram that I give people. Reactants in equilibrium with products. All right? Now, when this is truly at equilibrium, say at 25 degrees in 1 atmosphere, then this would have a Kc value at 25 degrees C and 1 atmosphere of pressure. This is your standard condition. At equilibrium versus reactants and products not at equilibrium at 25 degrees. So this is going to shift left or right depending on what I've just shown you in terms of gain, loss of weight, and what have you by the... So it will shift. Well, the K expression or the equilibrium expression is no longer called a K value. It's called a Q value. QC value in this case. QC values mean you are not at equilibrium. Now, QC is calculated the same way as Kc values, or K values. Concentration of the products over the concentration of the reactants. The same way. But it's not equal to the Kc value. QC is not equal to Kc. It's either greater than, less than. In some cases, it turns out to be equal, as in the problems here, and which means the QC is the Kc, and that's equilibrium. Well, to determine the nature of shift, you compare Kc with QC from the data that's given. We'll use the reactants products issue. And that's our reaction that'll given. In each one of these problems, you'll see the reaction that's given. Now, the way I'm asking you to write this is very important in you understanding the rule. Who comes first in the alphabet, K or Q?
Okay.
K, obviously. So you write 3 Ks first, a KC, KC, and KC. And then over here on the right, you write QC 3 times. Now the textbook gives QC first, but I have a ulterior motive, of course, in this. Then you put inequalities on the first one, the last one, and an equal sign in the middle, like that. Now that's an easy structure. You can remember that if you try. You put K first, followed by Q, and then inequalities top and bottom. Doesn't matter if you put them in that order, but the one in the middle is equilibrium. If when you make a calculation of QC from this problem, it turns out to equal KC, which they will give, then system is at equilibrium. However, if you make a calculation such that Q, listen to this, and so you'll understand what I'm trying to teach you here. If QC is greater than KC, then this means the reaction shifts left, or left shift. Notice the inequality that I've drawn. It points in the direction of the shift. So if you set it up K before Q and put this in like that, whether it's top or bottom, this one will show a right shift. So if you have QC calculation less than the KC value given, then you have a right shift in that particular reaction. Now, that's an easy table to remember and apply. Now it goes reactants to products, left to right. Now you typically write it in that context. So let's see how this is applied to a. Of course, we want to calculate KC and then compare it to the QC. KC is given in the problem to equal 3.07 times 10 to the minus 4, and we want to compare that to QC using the relationships that I showed you, and that is calculated the same way as in expression wise, the same way as the KC, products over reactants. So you see, you recognize that as the product of the concentration of the products divided by the product concentration of reactants raised to the respective coefficient powers. Then we substitute in the values that we are given up here. For NO, we see it is 0.0162, and we want to square that number. And bromine is a 0.0123 molar. We dropped the units because we're just looking for the magnitude number, and 0.0720, and that one is also squared per the expression, and it turns out this is, I just did it, 6.2 times 10 to the minus 4. Now that's your QC value. So when we look at the relationship or compare the QC to the KC, what do we want first? We want to write down QC. What I do is I simply start with KC equals whatever's given, 3.07 times 10 to the minus 4, leave a space in here, write down my QC value, and look at what's bigger or smaller. So when I look at this, it looks like QC is bigger than KC, so which way is it going to shift?
To the right. Left.
That's correct. So how simple that is, once you see that relationship, if you put the K first and then follow with the Q, it points in the direction of, well, you're assuming you write, I'm assuming you write the reaction, reactants go to products, okay? In that context. And then once you look at the numbers, you can tell who's larger or smaller, and then write your inequality and say, okay, it shifts left or shifts right, or if it comes out equal, you're already at equilibrium. Okay, that makes sense, guys? Okay, it's really simple, and your problems on the exam will be pretty much the same. Now, the only twists that show up in stuff like this, if the data comes to you in solution data, and it gives you so much molarity times volume, where you have to mix everybody together and then come out with a concentration term. And so, you know, you can get kind of involved when you start mixing up the data. But you ultimately want to get concentration terms in moles per liter and then apply it to the ratio, products over reactants, and then compare it to the K value. They have to give you the K value or the problem's invalid. You just can't make up a K value.
Dr. Flores.
Okay, let me ID this problem. This is 1461C, heading 9th. That's it. Let's see, 0134 and 0181. That's correct. So how do you set it up? Products over reactants, right? So QC is NO squared BR subscript 2 and NO BR squared, and substitute the values 0. Squared I get 3.06 times 10 to the minus 4. Well, in the problem, again, we're given the Kc to equal 3.07 times, let me see what I might say that rounds to an 07 times 10 to the minus 4. QC turns out to be the same number, times 10 to the minus 4, so they're equal. So reaction is at equilibrium. To understand temperature effects and how the reaction shifts as you change reaction conditions, you have to understand what we call thermochemical equations, the notations and what they mean. So we begin this with thermochemical equation symbology. So you have two kinds of thermochemical equations, the endothermic equation and the exothermic. We'll start with the endothermic. So we'll use the same AB system. Now, an endothermic reaction can be written, say, A plus B, and if at equilibrium, C plus D, and then you can separate the energy number. It's called the enthalpy, or heat of reaction. And we'll detail this. If you had my Chem 1, you would recognize that. And typically for an endothermic reaction, this number will be greater than 0, i.e., that is positive. Whatever it is. Example would be evaporation of water. You have to put energy into the system at equilibrium. Say this is boiling, and delta H of this reaction is equal to 44 kilojoules. So I don't put a signage in there, but it is a positive 44 kilojoules. Now, a second way to write these reactions is to incorporate the energy number into the equation. And to incorporate the number into the equation, if it's an endothermic reaction, we put that on the reactant side. That is A plus B plus whatever that energy number is for that reaction, plus that energy number, regardless of whether it's endothermic or exothermic in this case. And these are standard condition numbers, equilibrium with C and D. Okay? You never put negative symbology in a chemical equation. You use plus whatever symbology you're putting into the equation. But to indicate this to be an endothermic reaction, you have to put it on the reactant side like this. Now, applying this to the example I gave you, we would put plus 44 kilojoules as such in this format, and H2O as a gas phase. So there's two ways to write it, and it's important this second way is what we'll use in our seesaw principle to define shifting of the equilibrium. All right. Exothermic indicates a loss of energy by the reacting system to the surroundings, but it would be listed as A plus B goes to C plus D, semicolon, and you detach the reaction energy, and you find that the value, if it's an endothermic reaction, is less than 0, and this represents a negative value. In writing it down. An example of this would be this reaction, N2 gas plus 3H2 gas goes to 2NH3 as a gas, and delta H of the reaction is equal to minus 91.8 kilojoules. So we have to put the negative in to indicate that. Of course, positive's not indicated. You put it in there, I don't care. But you have to put the negative in. Now, if you wish to write this incorporated into the equation, you put the energy number on the product side as is giving off energy. So a second way to write this would be A plus B in equilibrium with C plus D plus the delta H of reaction number, like this. Or in the example that I'm given, N2 gas plus 3H2 gas in equilibrium with the ammonia, plus, see, I don't use a negative sign here, plus 91.8 kilojoules. The fact that I put it on the right side is sufficient enough to say this reaction is an exothermic reaction. Okay, so it's very important that you understand especially the second notation format where the energy value is incorporated into the equation. You want to think of this as endothermic reaction temperature effects. Now, when you write an endothermic reaction, of course, A plus B plus the energy number has to go on the reactant side in this format, and goes to C plus D. Now, the effect of temperature is heating or cooling. So on the left side, we're dealing with heating, and on the right example, cooling. We're running the reaction at a lower system temperature, or you're running the reaction at a higher system temperature. What you need to do to understand the tilt factor now is when heating, you think in terms of adding caloric matter. Now, energy is not material, but you have to think about it in terms of a material object. So heating is adding caloric matter is what I call it. CHLORIC. The heat flow used to be called caloric many years ago, and hence the evolution of the calorie and some of the terminology in history. But what you should think of in adding caloric matter is you are adding weight to wherever the delta H is placed in the equation. Now, you're not really changing the number. You don't change the number at all. It stays the same. But if you think about it in terms of, well, if this is over on the left side and it's getting heavier on the left side, which way is it going to tilt? That's the point I'm trying to make. So the tilt would be to the left because the left side is heavier. NDA plus B plus delta H equilibrium with C plus D. Well, it's not an equilibrium anymore, I'm sorry. So the reaction would have to shift to, it would tilt left, shift right. And ultimately create a new equilibrium, A plus B plus delta H, C plus D, and this would be your new equilibrium. If you can see that up there, that says new equilibrium. So the same effect is applied to the cooling side of our issue. So you look at it in terms of taking caloric weight out of the reactant side. It gets lighter, removes caloric weight, and you have a from delta H value, and it results in a right tilt. Now let me draw the reaction. And shifts to the left, and C plus D. So it tilts right, and you have your new equilibrium. And of course you got your energy number in there, like that. Well, the exothermic performs just the opposite. Now, you of course have to know if it's endothermic or exothermic when you start the problem. And then you mentally look at, well, what are they asking me? Are you heating the problem, the equation, or are you cooling it? And what's going to happen if I do these, whatever's in the So here's our hypothetical reaction, and for an exothermic reaction, we see the delta H number located on the right side of the equation. Then we ask ourselves, well, what happens if we heat this? What happens if we cool the reaction system? So if we're heating, it's going to add weight to that delta H number. So it's going to tilt right and shift left. And then you will form the new equilibrium in that format. So you'll notice that this is just opposite of what the endothermic reaction would do for heating, because we get the delta H number on the different side. And then if you cool it, you find the delta H, we're removing caloric from the right side of the equation. So if we remove it, then we'll have a tilt left, shift right. To regenerate the new equilibrium. And so that's how temperature effects work. I'm running out of time, so I'm going to push this on. Okay, we're talking real quickly about the pressure volume effects on equilibrium stability. Now, this is a Boyle's law concept in which pressure is proportional to 1 over V, or V is proportional to 1 over P. It's an inverse relationship. That is, increase pressure, you decrease volume of gas phase reaction systems. So this is your empirical change that you are considering in this effect on equilibrium. Now, this does not utilize the seesaw effect in the same way that we use it for temperature and concentrations. We won't have visible increases in masses or things of that nature to cause a tilt. Here we talk about molar volumes. Now, the pressure volume effects applies to gas phase components the reaction. Since liquids and solids are, for this purpose, incompressible, they are not taken into account. You can't change the pressure, volume, effects of solids and liquids, so Really, they're excluded. Now, having said that, I'm going to use two equations and show you how they are applied in the rules that go with the pressure volume effects. We'll start with 2NOBr, nitrosyl bromide, as a gas in equilibrium with 2NO gas plus Br2 as a gas. Right here. Now, and then we'll use 3H2 as a gas plus N2 as a gas to illustrate the kind of the other effect. 2NH3 ammonia gas. In the first reaction here, the number of molar volumes, we're talking about 2 moles of nitrosyl bromide. Well, that's 2 molar volumes here. On the product side, we're 2 moles of nitrogen oxide and 1 mole of molecular bromide. Adding them together, 2 and 1, is 3 total molar volumes of product over here. Now, in the second equation, we see 3 and 1 are 4 molar volumes in this one, and only 2 molar volumes on the product side. When we talk about these in terms of sum of molar volumes, we call this the high side because it's the larger molar volume, and this is the low side, so to speak. In this one, the reactant side is the high side, and this one is the low side. So in the format of this, you first need to understand the terminology and what you're looking at in the chemical reactions that we're working with. Okay, so move this up to here. So the rules are simple then. Once you understand this, what you're looking at in terms of the equation, then increasing pressure and at the same time reducing, see, the Boyle's law effect is an inverse. If you increase pressure, you have to decrease, it does the opposite, volume. Shifts reaction to low side. So when we talk about increasing pressure on this first reaction like this, it would shift left because it says it shifts to the low side. Or if we had the second reaction under consideration, then increasing pressure would shift to the right side and make more ammonia in that case. So decreasing pressure or increasing volume just does the opposite. So those are the two simple rules of dealing with gas phase reactions. And you only look at them from that gas phase component. Now, to bring all this together, what is the story on application? The application is to help you if you're an engineer, chemical engineer, for example, you want to increase the yield of your product. You apply these factors to the reaction system you're using to either increase or decrease, if necessary, the outcome of a reaction. Okay, it says, I'm going to rephrase the question so I can apply all of them at one time. We're running out of time. All the factors at one time. Okay, methanol is prepared industrially from the synthesis of carbon monoxide and hydrogen gas. So the equation that we're using is CO as gas plus 2H2 as a gas is in equilibrium with methanol, CH3OH, and is written as a delta H negative 21.7, but I'm going to incorporate it, so that's plus 21.7 kilojoules. I'm going to put it into the equation like this. Now, in part of this, so put the reaction that you have on the seesaw for the purposes. So the question is in this reaction is, how do you go about increasing the methanol concentration? They're all gas phase. I forgot to put gas on that. Let me put that. Very important that you put the phases in so that you can apply that pressure volume effect in this problem. Okay, so what are the factors that will affect this reaction? Now, if the question is, how do you increase this, that means whatever you do in factors has to shift the reaction right. That's what we're trying to do, shift right. Increases that concentration. Yes, I mean, it's logical, isn't it? So I want that to increase. Okay? So I want to look at concentration effects. What would I apply to this reaction in terms of the seesaw effect as it applies to the concentration rules? Okay? Temperature effects. Would I run it at a cooler temperature or a higher temperature to make more methanol? Or what about your pressure volume effects? Would I run it at a higher pressure or would I run it at a lower pressure? So when I look at this concentration effects, if I want this reaction to shift to the right, I need a tilt left. Okay? So one is to increase reactant concentrations. It's called the feed. Increase the feed of your reactants. Or if you want to keep the reactant feed constant, or remove products as the product is generated. Because removing the product would tilt left, shift right. You want tilt left, and then shift right. Okay, so you have two options in that case. Now, temperature, what is it? It's on the right side, it is endo or exo? Exo. So increasing temperature, decreasing temperature is your option here. So if you increase, that wouldn't help you, would it? Because it would tilt right, shift left. That's not increasing the methanol. So in your temperature effects, I want to run at reaction at a lower temperature. Because what you're trying to do is remove caloric from the number, making it lighter, and tilt left, shift right. And in the pressure volume, when you look at the numbers, coefficient numbers, we have on the reactant side 3 molar volumes and 1 molar volume over here, and we want to shift right. So what is the rule that says to shift right to the low side, right? Would I increase or decrease pressure? Increase pressure. So increasing pressure shifts right to low side and increases CH3OH yield. And that's how you apply Le Chatelier's principle in the context that we're working with at this point. You take the reaction and ask yourself, well, I want to increase this. All right, even if you make a decision to decrease it, decrease the product yield, what would you do? Well, you do the same application of rules and come up with, well, I change the concentration over here and what have you. And you first determine the tilt and shift, or in the pressure, who's the high side, low side. Okay, that brings us to the end of chemical equilibrium basics. Okay, there are other problems in here. Please go through them. If you've got questions, I ask you to send them to me. I'm not getting much response from you people. You better not assume anything. Okay? I may not have the magnetic personality you think I got. Yeah, right. Okay. Anyway, please invest your life now, because when you get my age, you're going to wish you had. Have a good day. Have a good day, sir. Set that bridge for me, sir. I will post this tonight.